Hey guys. Yeah, Polly started today's lecture early. Yeah, just slightly early. All right, so let's go through the announcements. Let me skip the first two bullets because they all look the same. So third says, oh, hi. Hi, Jeremy. Yeah, handler. What does that mean? Or handle, what does that mean, right? Jeremy. Yeah, I meant something a little bit more general. Hey, Sylvain. Okay. Yeah, good afternoon, all. Yeah, this week, again, Polly might be a little bit too ambitious saying that there are 3 quizzes doing. I think chances high that we'll just do 2 quizzes this week. Okay, you will see also why. Oh, hi, Jiabao, Miguel Tao, Zhiyu. And I do have it here, bullet 4. PA number 3. I see some of the teams completing PA3 already. Wow, okay. But I know that some of you are working on it and struggling with it a little bit. You want to start early. And guys, test your file upload client, which is what PA3 asks you to do, using the test file. Okay, I've already inserted. Okay, as root of the workstation, I get to do anything I want. Okay, so I put actually this file into your directory. Use this file to test. Otherwise, you run into a lot of trouble. That's not necessary. Okay. Number 5. Okay, so here I provide the link to a set of videos that explains this thing called public key encryption. Okay, the reason for this link is that the first topic today will talk about secure transport, and that protocol requires knowledge of public key encryption. So in case you had trouble understanding the first topic today, go watch this video series first and then come back to the video of topic 1. Last and the worst. Oh, tomorrow is the Teacher's Day. I mean, on one hand, I'm the teacher, right? So that is supposed to celebrate me. But we don't get to lecture, we'll be behind. So I guess this semester, similarly, the first exam scope will be narrower than what I would have wanted. All right. So hi to you all. Hi. Okay. Yeah, so this is Polly crashing, mental breakdown there. All right. Without further ado, first topic. Okay, so I'm gonna rush a little bit today. Okay, so no lecture tomorrow. Thank you, Zhenyu. So first topic, secure transport. If you recall last week, we talked about 2 transport layer support, right? One is TCP, the other UDP. TCP helps in terms of reliability. UDP helps in terms of timing, QoS, in terms of throughput, QoS. But you know what? We have the 4th QoS, security, right? But none of TCP, UDP support security. And you know what? There's a 3rd transport support that is called secure transport. So this video talks about the protocol SSL. Nowadays we call it TLS. That will do that would do secure TCP. All right, secure TCP. This is the next topic. Yeah, if you recall, when we're talking about these service requirements, right, there are 4 of them. Reliability, which is supported by the TCP. Delay requirement, right, which is somewhat supported by using UDP. Bandwidth requirement, and that might be better supported by UDP, but TCP might do a reasonable job. But the 4th, security. Yeah, the fact is that TCP and UDP, none of them provide security. There's no encryption at all. If we send passwords through the internet straight using TCP or UDP, it's essentially clear text. If there's someone intercepting the message, that someone gets access to our bank accounts or gets into our Amazon.com's account. So none of these cases is good. Big money loss potentially involved. So demand is growing, therefore there is need of these secure layers. So this is secure socket layer. So what it means is that before messages go through the socket and go out on the internet, let's make sure that it's secure. Okay, so it's to provide encryption to messages that's going into a TCP socket. As a result, then we can encrypt messages using a key, or we could verify the receiver using a certificate. Okay. So this is just as important as trying to make sure that the data is confidential, okay? Because how do you know if this server that you are contacting to is indeed a Google server, right? How do you know if it's indeed your bank's server? So this is to identify whether the person you're talking to is indeed the person you're expecting. This is just to make sure that no one can understand the message. No third person can understand the message. Okay. And SSL is at application layer. Yeah, it's on top of TCP, therefore it falls in the application layer. But it's also right underneath the application layer protocol, so message go through the application layer protocol, and then to the SSL, and then to TCP. Okay, so this picture below illustrates what I meant here. So SSL right here, right underneath the application layer protocol, but right above the transport layer protocol. Last, SSL socket API. Yeah, to implement SSL, there are APIs available for each programming languages. In chapter A, you will see Python's API to try to encrypt messages before they send messages out onto TCP socket. Now, in this semester, towards the end, one of the PAs, you will also be exercising the APIs in Golang to do secure TCP. But there, we'll be using this, TLS, Transport Layer Security Support. Yeah, this is actually a newer term for SSL. So nowadays, people don't call the security support over TCP SSL. They are all referred to as the TLS, okay? If you think about it, this makes a lot of sense because, hey, SSL there is not really a layer. It's more a support for security, all right? Okay, so that's the overview. Next is the detail of the TLS, exactly how that secure layer works. Okay, so this one is the one that I mentioned intensive. You might need the knowledge of public key encryption. And by the way, excuse Polly's camera. So you will see Polly in the middle of the video get frozen. Okay, so TLS, this next video. Next, let's explain how TLS works. Before that, let me go back to the very fundamental computer security. How do you encrypt a message such that it can be kept as a secret? So the classic approach is the secret key mechanism. So what we do there is to generate a key, and we share the key with Bob and Alice. So when Alice has a message to send, yeah, use that key K, apply the encryption function, and it's going to generate something that's messy. So a third party in the middle here might intercept the message, but without knowing the key, it's not able to decrypt it. Bob, on the other hand, receiving the messy message, using the key, can restore the original message. Okay, so this is the classic secret key communication. Unfortunately, the secret key system will not work to implement TLS. If you think about it, we have one shared secret key. Let's say if Alice is the one generating the secret key, Alice is yet to send the secret key to Bob, isn't it? I mean, didn't we need TLS because we fear we send password in clear text to the other end? So Alice here is sending the shared secret key in clear text to Bob. Same problem. Yeah, so we do have a bootstrap problem with the secret key. Now, to address that problem, we use this other system on top of secret key. It's called the public key system. So instead of using one shared key, public key system generates a key pair. One is called the private key, the other is called the public key. All right, so the receiver of the secret message is over here. Sender of the secret message is on the other side. What the sender does is to plug the message she wants to send, and then encrypt it with the receiver's public key. Yeah, the reason that it's called the public key is exactly because R is going to give out that key to the public, including the sender here. So this is going to scramble the origin. So this function is essentially scrambling the original bits here using this particular parameter. So the encrypted message, as it arrives at the receiver there, then apply the same function and take the receive message, and receiver can decrypt with the other key in the key pair. So this is going to give the original message back. Now, the private key is the one kept by the receiver, and no one else in the world will know. Therefore, you ensure that no one else will be able to decrypt the encrypted message. So only the receiver can see the original message. So this is how the public key ensure secret exchange. So TLS illustrated up here works this way. Alice here is a client requesting service from Bob here, a server. So client here first sends hello message to the server. Server in response sends server's public key. So Alice here can then encrypt the shared secret that has been generated before using Bob's public key. So Bob's public key here. Then encrypted master key will arrive at the Bob side. And because Bob is the only one holding the Bob's private key, therefore Bob can restore the master key from EMS. And that's how Bob and Alice establishes the shared secret key. So in this case, you see Alice is the one generating the secret key. And from then on, all the messages are encrypted using the master secret key. And that's how TLS worked. All right, makes sense. Yeah, interesting, isn't it? The public key system. All right, so that's chapter 2.1. Okay, so we'll be switching gear about how we talk about the application layers. So let me ask you to recall your learning experience in the past. A lot of time we learn new things by, for example, learning the terminology first, the concept first, and then maybe a little bit of theory. But in many other experiences, we learn by seeing lots of examples. And the human brain somehow is magical in a way that when you see enough of these examples, you kind of pick up how things work, isn't it? For those who are more aware, the way we learn circuit programming using Golan is exactly learning by example. It can be quite effective depending on your personality and how your brain works. You know what? Chapter 2 is also organized this way. 2.1 talks about the terminology, the concepts. Okay. Starting from 2.2, Polly will be introducing many examples. Okay. One application and introducing the protocol supporting the application at the time. And so up next is the first application, web browsing. And the protocol supporting web browsing is called HTTP. So this video talks about the basic of HTTP. Hey, recall, right? What are the design elements when you need to, work on a network application? Architecture, communication model, socket, and messages. So in this video, you will see how HTTP architecture is like and how the entities communicate to each other and what kind of socket it uses. Web and HTTP. Let's do a quick review. Web is essentially a bunch of these web pages interconnected. So each web page consists of a number of objects. The base object is typically a HTML file. And then in each file embedded are several referenced objects. And these objects could be another HTML file, could be a JPEG image, could be an applet or a script or an audio file. Each object on the internet, on the web, is addressed by the URL. So this is an example of the URL. There are three parts: the host name, and the path, and the file name. Okay. And the HTTP protocol there to support the web application runs in the client-server model. So the client here are essentially the browsers. The browsers is essentially requesting for web objects and then in turn receiving web objects, of course, using the HTTP protocol. Now another task the browser does is displaying the web objects. Just to clarify, passing of these messages and web object is the HTTP protocol's job, but displaying web object is actually something else's job. It's the HTML interpreter's job. Yeah, so HTML interpreter is not quite the HTTP protocol. So you see here, a browser, that program there, is a combination of the HTTP protocol client-side and an HTML interpreter. So this interpreter is to interpret the HTML page because there are some markups around. Based on the markup, the interpreter will know how to display a web object so that it appears properly and nicely. Now the server, web server, very few of you guys have experience building your web server, I suppose. Yeah, so in this example we see Apache, I think is still the most used server, but this guy here is catching up, Nginx. Both of these servers are implemented using C and C++ socket, all right? So the web server implements server side of the HTTP protocol. So what it does is to receive requests and send back response. So that's the exact opposite of the client. It's to receive objects and send requests. So let's see the exchange. So this client up here, sending HTTP requests and then receiving the HTTP response, and containing the HTTP response is the web object. Similarly, if it's a phone, yeah, Safari sending HTTP request and server sends back an object and Safari renders and displays the object. All right, so that's HTTP, Hypertext Transfer Protocol, HTTP. And HTTP runs on top of this transport layer protocol, TCP. And the whole process is actually this. First, tries to establish a TCP connection between the web server and the web client, and then sends the HTTP messages. So before the client and server sends HTTP messages, the client and the server sends TCP messages first. So starting from the client, initiating a TCP connection. Now, if this is a web server sitting on the default port, it's going to be port 80. And then server would accept the TCP connection, inform the client, and then client can begin sending the HTTP request. And the server sends back HTTP response. When everything is done, the TCP connection will be closed. Know that HTTP, as you see, very simple, request response. In fact, each of these requests is treated as brand new, it's very fresh. That means what the server is doing there is to not record anything about the client. So there's no information about the past client requests. Okay? And we call this type of a service a stateless service. So on the server side, there's no requirement of storing anything about the client. So this is really nice because the server does not require a lot of memory space for these information. All right. Yeah, protocols that maintain states can be complex, so this is the other extreme. You might need to maintain the past history, which can be long. And you might need to maintain history for multiple clients. How about that? Yeah, that's a lot of burden in terms of a memory space requirement. And besides the service load, the memory requirement, what if the server and client each crash while the other continues to run? Then the states on the two sides might be inconsistent, and they will have to resolve the conflict somehow. That's the worst, right? So should you trust the client or should you trust the server? This is one of the classic car problems, all right? Yeah, so that's the basics. And it sounds like the exchange between the client and server is very simple, right? Client server first pass some messages so that we can establish that TCP connection. Second, send messages, right? Request object, returning of the object, and then close connection. Okay. That is just the basic mode of the HTTP connection. Till now, there are already 3 generations of this connection modes. Okay, this next video is going to introduce each one of these 3 modes. Connection mode. HTTP connections. There are actually 3 flavors of HTTP connections: non-persistent HTTP, persistent HTTP, and third, persistent HTTP plus pipelining. All right, so let's start from the most basic, the oldest flavor, non-persistent HTTP. This is implemented in the pioneer versions of HTTP, let me call it that way. In that, you send one object per TCP connection. So the clients and the server sets up a TCP connection, and then you send one HTTP request, you get one web object, and then you close the connection right after that. So to download multiple objects, you need to create multiple connections one after another sequentially. Now in persistent HTTP, the main idea is, well, why do we keep opening TCP connections and closing them? Why don't we just reuse the TCP connection we have started in the first place? So in persistent HTTP, client and server establish the TCP connection, and then first web object exchange, second web object request, and the object response exchange, and so on and so forth. So one single connection to send all the objects. All right. Now, the basic persistent HTTP mode works more like that. So you have one exchange to establish TCP connection, and then it's just object 1 and object 2, and then object 3. Okay. But the thing is this: when we establish the TCP connection and sending out the first request for object 1, really, before the object 1 is being transmitted back, you see, client over here, it needs only this amount of time to send the request message, right? Client is immediately left idle right after that. So why don't we send the second object's request, the third object's request, and the fourth object's request subsequently and immediately? That way, you just need another exchange like this and just a few more transmission time. Then we're done with everything. Unlike here, for each object, you need this much time, and the second object will wait this much time, and the third object waits even more time. Okay, so this here is the persistent HTTP plus pipelining. Nowadays, when people say persistent HTTP, the implication is that, hey, it's persistent HTTP with pipelining. And by the way, this is HTTP, the 0.9 version. And persistent HTTP without pipelining, that's the HTTP 1.0 version. And the one with the pipelining is the HTTP 1.1 version. All right. Now let's go through the animation for the very standard non-persistent HTTP protocol's behavior. Let's suppose we are looking for this object here. So the URL contains the host name, the path, and the file name. And let's see that this base file here contains 10 reference objects. So there are 10 images embedded. Step number 1, the TCP establishment. Client here initiates connection request. Server sitting at this location at port 80 will accept the connection and then send back a sure, open it message. Second exchange is the client sending the request message. All right, so in the message embedded is the URL. All right, so that's going to go through the socket, and URL right there in the message. Server will receive the message and sees the URL, finds the path, finds the file name, and therefore extracting content and generate the response message. And that response message is shoved again through the socket back to the client. Now, immediately after the response is sent, the server closes the TCP connection. HTTP client here receives the response, parse the HTML file and displays it, And in that process, it's discovered that there are 10 more reference objects to download. And the client then will repeat step 1 to 5 again and again and again, 10 times until all 10 objects are downloaded. All right, so 3 modes. Okay, I hope it's clear. And you can probably see that from the oldest mode to the newest mode, the efficiency gets better. And that metric we use to measure the efficiency is called the response time. So next video formally define the response time. It's how fast we manage to download all the objects we want. And the time to do that is pretty long. Let's try to count the amount of time to complete the entire download. And we call that the time to download an entire page being the response time. Before calculating it, let's define this term. RTT, which stands for round trip time. It is the time for a small packet goes out to the other end and comes back, out and back. So it's a round trip in a sense. So client over here, server over here, to initiate a TCP connection, the connection request go, connection established, granted messages come, that's 1 round trip time, right? So 1 round trip time for initiating the TCP connection. And it's another round trip time to send HTTP request and receiving the HTTP response. So this part is 1 round trip time. But the dark, thick square here, this is the time it takes to transmit the file. Okay. So when the object is very small, this is very narrow. When the object is large, this could also be quite wide. So let me fill it up. Yeah. So the object itself could be big, the transmission time can be long. So the shadow part is the file transmission time. So the response time to download just one object using non-persistent HTTP is 2 round trip time. 1 here, 2 here, and then the file transmission time. Now we can try to account the response time for that page we were loading, the something.edu, the object there. So we have the base and then 10 more objects. So altogether 11 objects. If we're running the non-persistent HTTP connection, then we have 2 round trip time plus the transmission time for object number 1, the base object. For each of the 10 objects, we do more. Okay, so the transmission time might vary a little bit from object to object, but round trip times remain the same. Right, so there are 10 of these. So 22 round trip time. So 10 of these plus this one over here, the base. And yeah, the sum of the TX. Okay, and depending on which object it is for all I. All right. Now, but for persistent HTTP, the server is going to leave the connection open after sending response. So subsequent HTTP messages between the client and server will be sent over the open connection. Client can send requests, as I said, right? Persistent HTTP without further clarification, it's the persistent HTTP with pipelining. So the client here will send all the 10 requests as soon as possible. Okay. So in the end, it's just 1 round trip time plus the transmission time of all these objects. So altogether, just 2 round trip time. First is to establish the connection. Second is to download the first object. Okay. Third is to download all the rest of the 10 objects. So it should be 3 round trip time plus the transmission time required to send all these objects. So 22 versus 3. Big win over here, right? Yeah. So this is in HTTP version 1.1, the most up-to-date version. And that takes us to the first quiz today, quiz 9. All right. So let's suppose we're downloading a web object that has 1 base HTML and embedded in this HTML 5 reference objects. Right. So let's ignore the transmission time. So Q1 asks, what is the response time in units of RTTs if we use a non-persistent HTTP? connection. Q2, for the same web object or web page, if we use persistent HTTP connection, so how long? And if we use the latest persistent without pipelining connection. Q4 is a little bit tricky. Okay, so what about non-persistent HTTP, which is the one that says establish TCP connection, send one object, and close the connection all the time. Okay, but in the meantime, we can do parallel connections. Let's assume you can use infinite number of parallel connections. So you could what? Yeah, start TCP connection, get all the objects you want at once. Okay, and if you are getting a base and there are 5 reference objects you need to fetch, then you start another TCP connection. But you can have 5 parallel TCP connections and getting all of the 5 objects at once. Okay, so what will be the delay like? Okay, for the force mode. All right, and let's move on to the score. Channel W4, quiz 9. This should be a straightforward problem, but you might need to derive the answers. But as a straightforward quiz, the first solvers get the bonus. All right. So how much time do we need? I think probably 3 minutes. Let's give it 3 minutes and start counting now. Yeah, I see you guys typing. Yeah, you're probably close. Hmm. Let's see who's gonna be the first. Oh, okay. Let's see. So team 9, Q1, 12 RTTs. Yeah, so the non-persistent HTTP mode says that we just start a TCP connection, get an object, and close. And there are 6 objects, 1 being the base, 5 being the embedded references. Yeah, 6 multiplied 2. And the second is persistent HTTP. By default, it's the pipelined version, right? That is, start the TCP connection, so one round trip time to create a TCP connection. And then, of course, 1 round trip time to get the base HTML. Without the base HTML, you don't have the URL to the reference objects. So you need to get this one first. And once you get the base HTML, then you can what? Send 5 requests, right? One after another, pipelined. And that will be another round trip time to get the rest of the objects. Yeah, I think I also have 3 RTTs. Let's see. Team 2 also get 3 RTTs. And Q3 is without pipelining. So it's the persistent connection without pipelining, without sending 5 requests back to back. Okay, so that means we start one round trip time to start the TCP connection, and 1 round trip time to get the base HTML, and then we send first request to get the first object first, and then the second request to get the second object. For each of the objects, it's 1 round trip time. Okay, so this is the difference between without pipelining and with pipelining. Okay, it's the 5 objects at the end. In pipelined mode, you get to do it in 1 round trip time. Otherwise, yeah, you need to do it in sequence, one after another. Now, parallel connections. Okay, again, we need to get the base first, and that's 2 round trip time to get the base. And then we have 5 objects. And with the parallel connections, and we can have infinite number of parallel connections, we just start 5 parallel TCP connections, right, to get the 5 objects. That's 2 round trip time as well. So, yeah. Simultaneously asking for a TCP connection and get an object. So that should add up to 4 round trip times. Yeah. And I see team 5 also come up with 12, 3, 7, 4. All right, good. So you guys get the idea. It sounded complicated, but it's in fact quite straightforward. All right, good. I see other teams now having a better idea, observing other solutions. But we need to move on. Okay, so hey guys, in the earlier videos, we hear about the architecture and the communication model, right? It's client-server based. And we open a TCP socket, okay, for the HTTP messages. Now, let's talk about the message types. We can now start sending messages. Let's start by talking about the message types and the format, okay? And request messages first. This first video is short, just to give you an example of what the request message looked like. Let's take a closer look at the syntax of HTTP request message. First is the request line. It's only a single line, 3 tokens, separated by 2 spaces, one over here and one over here. First token indicates the command the client is issuing to the server. So get here is the most classic command. Second token here indicates which object the client is wishing to download. So here you see the path and the file name of the object. Third token is very straightforward. It's simply telling the server the version of the HTTP protocol the client is implementing. Now, header lines. Syntax is also quite straightforward. Column in the middle. Before the column, this is called the attribute or the field name. And whatever comes after the column is the value of the attribute or the value of the field name. All right, so user agent is a well-defined attribute in HTTP. It indicates what implementation the browser is and the version of it. So user agent indicating the meaning being user is using a browsing agent called Firefox, and it's version 3.6.10 of Firefox. Okay, similarly, okay, keep alive also a predefined attribute. And the value 115 is saying that let's keep the connection alive for 115 seconds if there are no messages being sent. Connection indicates the type of connection the client is wishing to establish. It's the keep alive kind of connection. And so you see the syntax and a little bit of semantics of HTTP requests. All right, so that's a simple example. And we had a question. Zhenyu wants to ask about head. Okay, it's one of these comments in the request line. And we'll talk about that in the third video about request message. Okay, now the second video, you see an example. Now the more general format. Okay, when the general format is introduced, Polly is going to talk about more comments you can use in the request line, just like the head. Next, the general format. Okay, now with that introduction, with a specific example of HTTP request, so this will be slightly easier. You see here, first is the request line. And then we get a whole bunch of these header lines, and it ends with what? CRLF. Okay, in fact, at the end of every line, CRLF, okay? And in the request line, we have three components: the method, the argument for the method, and the version. Okay. Some comments might not contain the second component, all right? And you see here, for each header line, we see what? Pair of attribute name and value. So in the slide, we see this is the header field name. So those attributes are sometimes also called the fields, the field names. So attribute value or field name value. Good. So lots of these. Okay. And hey, this is the thing that we did not see in the previous example. Yeah. Occasionally, you do need to have a body in the HTTP request message. And this is what, if you recall, the post comment. We're sometimes posting content, posting data onto the server. So those data, those information to be communicated from the client and to be registered at the server will be here in the entity body. So real data generated by the user is here. Okay. So officially, in general form, the HTTP request comes in three parts: request line, header lines, and body. But for most of the HTTP requests, there are just two parts: the request line and the header lines. Now, let me add a little bit more. First, the post method. You've heard me. There are sometimes web pages that you need to fill forms, okay? Input names, usernames, potential passwords. Okay, those input are uploaded to the server in the entity body. There's another way of doing that recently. Okay? It's called the URL method instead of the post method. What you do there is, hey, you could be clicking just buttons, okay? A certain link, in fact. What the browser does there behind the scene is more like this, okay? Requesting to the server, all right, okay? But it's actually sending a phrase like this. Instead of a file name with a path, okay? So instead of having a path, something, and then something.html. So it's a very weird form of HTTP request, okay? While we know this is more classical, but these days we see this more. Okay. Animal search question mark and then something and something. Okay. So this is actually a query. Okay. Unlike request sounds more like requesting for a service, requesting for a file, for an object. But clients often query the server for a service. Okay, for example, look up a database. Exactly. So in a way, the World Wide Web is evolving from a huge hard disk, a global distributed hard disk, to a global distributed database. Okay, so in the HTTP request there, we are actually sending a query. This is the name of the query. And this is the input to the query. So this query obviously contains two arguments in order to execute, for the server to execute. All right. It's using the get method instead of the post method earlier. So this type of a service request is using the get method, but in HTTP request message. And the input is exactly in the URL field in the request line. Okay, and it's this way. Yeah, the query name and then the arguments for the query. All right. Okay, good. And here, to answer your question, Zhenyu, there are many other comments or in the videos or formally should be method. That's actually to the first thing in the request line to let the server know what the client wants. Sometimes it's to get an object. Sometimes it's to post an object. Sometimes it's just to get something based on a certain query. Okay, and head is also the client wants the server to do something. Okay, so in this last video about request message, probably inventory all these methods in generations of HTTP and explain how they work. And the last slide about HTTP request here is quite straightforward. What it says is to tell you again what are the comments, okay, possible in HTTP request line. In version 1.0, we see get, we see post, we see head again. Okay. But this is all that HTTP 1.0 supports. In HTTP 1.1, we extend the comment options from the 3 classic ones to add 2 more, put and delete. Okay, let's go through these 3 other comments. First, the head comment. So this is usually for a web client to send sort of initial HTTP request to the server, and server will send some response back, but only to tell the status of the server or the specifications of the web server, and leave the actual web object the client is asking for out of the response, so that the response is very short. And what's contained in the response messages are just all the essentials, like, you know, what is the version of the web server program you're running over there? What is your IP address? What is the time date? What is the time date, the object that the client is asking for being modified last? Okay, things like that, the essentials about the server, about the object, so that when the client receives a response like that, the client can plan a little bit better ahead of time how the client does the requesting. Sometimes when the file is really large, the client might try to dissect and then do the requesting slightly differently. And put here, this one is actually quite forward, just to upload the file in the entity body of the HTTP request to the server, right? So in that request, we also specify which path in the server we want to upload this file to. Okay, so it's working pretty much like the FTP. If you recall FileZilla, you are dragging a file to the server, right? So it's uploading a file to a specific path on the server side. So put here implements file upload. Delete, deleting a file. So FileZilla also allow you to do this. So essentially, HTTP 1.1 is to extend the original HTTP to include all the file uploading, downloading services, because the original HTTP only does file downloading, not quite the uploading. Now, when HTTP 1.1 is available, FTP protocol quickly loses its popularity. Okay? And that's why we rarely use FTP these days, because HTTP, the web browsers can do all these for you. All right, so this is HTTP request. And that takes us to quiz 10. And please allow me 2 minutes to introduce quiz 10. And quiz 10 is going to be a take-home quiz. Okay, so there's no hurry to provide your solution. We'll not be giving bonus based on the speed of providing the answer, because many of you might need to rush and go to the next lectures. Now, what is quiz 10? One can use a traffic sniffer such as Wingdump, Wireshark, or if you are a Unix user, TCP dump, to actually sniff packets going over your network interface. Okay, so Polly actually sniffed one of the messages that I generated by clicking a link on my browser. Okay, and this is the content of that HTTP request message. And it's obviously a GET message. Yeah, hi, Hashem. And Q1 ask, so observe the content. What is the URL of the object being requested? Okay, and how did you know that's the URL? Q2, is it non-persistent or a persistent connection being used here, connecting the browser to the server? And how did you tell? All right, so those are the quizzes. Okay, but the key point here I want to show is, hey, these HTTP messages, they are in plain text. You can sniff and see what's in there. Okay. Now, if you use HTTPS, then they'll be encrypted. All right, good. So that's all for today. This is a take-home quiz, so take your time. And with that, I say goodbye. Okay, no class tomorrow. There's actually no class on Friday, right? That's the Mid-Autumn Festival day. So enjoy the holiday, enjoy the long weekend. Okay, bye. All right, go out. Oh, same to you, Sophia. Yeah, I think the weather is gonna be nice. Okay, be cool to go places. Yeah. Bye-bye. Yeah, you too, Isa. Okay, guys. Call your friends up. Yeah, go somewhere. Okay, bye.